From Diamond Light Source, this is the Diamond Podcast.
Hello and welcome to the April edition of the Diamond Light Source Podcast. This month, we're drawing your attention in with magnetic force as we go down to atomic scales and investigate the properties of magnetism. We'll be investigating the different forms of magnet and magnetic materials to see how they work, what applications they have, how they can increase our understanding of phenomena such as superconductors, and how properties can be made to change in a class of materials known as multiferroics.
So we're hoping to use these materials to store information in a magnetic form and then to change the state of information, say from 0 to 1 in a bit, but rather than doing it by applying a magnetic field, we could apply an electric field, which is much more localized, it has low energy consumption, and we can have a much more compact, faster, overall better system.
Paolo Rodelli will be explaining how these materials could provide a new form of data processing and storage later in the programme, when we also bring you the latest news and events from Diamond. So all that coming up in this Diamond Light Source podcast with me, Mira Senthilingam.
The Diamond Podcast. For more information, look us up online at diamond.ac.uk/podcast.
Magnetism is a word we've all heard of. Many of us may think of the horseshoe magnets that cause metals such as iron to fly towards them, or else the bar magnets we may have come across in science lessons at school. The forces we see here are down to the presence of magnetic fields, which can be permanently found in certain materials or else induced in others, causing the attraction and repulsion we then see. A good insight into the workings of magnets and magnetic fields can benefit a wide range of technologies we rely on heavily today, such as data storage. Steve Collins is the principal beamline scientist on Diamond's Materials and Magnetism beamline, and he gave me an introduction to the properties and features of magnetic materials.
Well, the most obvious and well-known form of magnetism is what we call ferromagnetism, where basically magnetic materials would stick together. And if you look on an atomic scale at what causes that, it's exactly the same thing, but on a much smaller length scale. So you have tiny magnetic atoms which are interacting with each other and all pointing in the same direction. But in fact, a lot of magnetic materials, they're pointing in other directions, and they tend to point towards each other or to find some other kind of exotic pattern of arrangement, so that on average, there's no net magnetic forces. And so you would say that the materials, at least from a ferromagnetic point of view, are non-magnetic, but on an atomic scale are very much magnetic and have interesting magnetic properties.
So that essentially comes down to charges on the atomic scale on individual atoms.
It does, exactly, but the important thing is not the static quality of the charges, but the fact that they're moving. And classically, you can think of almost a planetary orbit of electrons around a nucleus, which is like a star, and they go round in a certain direction. You can imagine that each atom has a north pole and a south pole. To understand the structure and the symmetries and the electronic properties of the materials on an atomic scale is absolutely crucial to understanding how the materials work.
And what about then the applications of this knowledge and this understanding of magnetism? What role does it play in, say, everyday society, such as, say, data storage?
Well, data storage clearly is the big growth area at the moment. And, of course, using powerful magnets for making electric motors. But increasingly, these very exotic magnetic structures are expected to find use in electronic devices.
And, well, Steve, you're principal beamline scientist here on the Materials and Magnetism beamline. What type of research is taking place at this beamline?
On this particular beamline, we look at the magnetic properties and related properties of materials really on atomic length scales. So we kind of combine the fairly conventional measurements of X-ray diffraction, which are used to understand the crystal structure of all sorts of materials in the physical and life sciences, to looking at relatively simple structures, but we look in much more detail and understand from these measurements exactly where the magnetism is on atomic scales. We can see where the magnetism is, we can see which atoms are magnetic, and we can even work out the cause of the magnetism in terms of whether it originates predominantly from the intrinsic magnetism of every electron which is in the material, or because of the motion of the electrons around the atom.
Well, we've come alongside your beamline now, and so there is a fine metal tube where the X-rays obviously come out, an area for the sample to actually be placed just in front of that tube, and then something that's kind of moving around it, which I imagine then picks up the scatters from the crystals.
It does, actually. This we call this a diffractometer, but it's effectively a large robot. The robot has two hands. One hand of the robot holds the sample that we're studying and moves it into the positions that we need, and the other hand of the robot will hold the equipment which detects the X-rays scattered from the sample, and we have to synchronize the movement of both the hands of this robot in order to carry out the measurements.
But now, looking at where the sample's actually mounted, there's a metal cylinder, and it looks like a fairly complicated piece of engineering just for where the sample's placed.
That's right, and this is because a lot of the materials that we're interested in have properties which change with temperature. The particular device that you're looking at can take us down to about 4 degrees above absolute zero in temperature.
So very cold.
Very cold.
And is there an example then of a sample that could be looked at, and what kind of diffraction it would cause when an X-ray hits it?
Well, a lot of the materials that we look at are materials that we call antiferromagnets, and in these materials the atomic scale magnets tend to point towards each other, but the important thing from the diffraction point of view is that they form extra periodicities in the sample, so it's very much like a diffraction grating. Like the diffraction of light that you would see from a CD or something like that. But because the magnetism forms an extra periodicity, it gives scattering at angles which would not see any scattering if the magnetism wasn't there. So the nice thing is we have a very, very clean signal which is showing us exactly the effect that we're interested in. So we can pick out either the magnetism or some related process and home in specifically on that.
And what kind of application then could this knowledge have?
Largely, almost entirely, in fact, in basic science, and it's a question of understanding the properties of the materials, so where all the magnetic moments are in a crystal, which directions they point, and also at the same time we often study any very small displacements. I mean, these are displacements of a very tiny fraction of the size of an atom, but the displacements can have a crucial effect on the properties of the materials, and we can see those using exactly the same equipment.
Steve Collins, Principal Beamline Scientist on Diamond's I-16 or Materials and Magnetism beamline. And the insight into fundamental science that Steve mentioned has a wide range of repercussions spilling out into the field of computing. Paolo Rodelli is a Professor of Experimental Philosophy at the University of Oxford, and he uses the beamline to study a class of materials known as multiferroics. These are materials that respond to both magnetic and electric fields, a response which results in a change in their properties, and an understanding of this change could enable better control of magnetic media in the future. Paolo explained more about these materials.
Essentially, multiferroics are materials that can be addressed using two different fields. Current materials can be read or written, but just based on their magnetic properties. But we know already Einstein's in the theory of relativity stipulated that really magnetism and electricity are two manifestations of the same phenomenon. They can be interchanged with each other if you have an object that goes to speeds comparable to the speed of light. And this is precisely the phenomenon that we are exploiting to create materials that can be read and written electrically, which is a much more efficient, energy efficient and faster way to address materials, but they can still hold the information magnetically, which is very, very efficient as well.
what would the benefits then be of this, say?
We can make electronic devices and in particular information storage as well as information processing devices that are smaller, they consume less energy. We all know how annoying it is to have a laptop that runs out of battery or an iPod that runs out of battery.
So multiferroic materials are materials where magnetism or electronic fields can be applied in order to change the magnetic properties.
Exactly. So the idea here is that you can apply an electric field rather than magnetic field and change the information state of a bit.
And so could you give some examples then of some multiferroic compounds or materials?
So multiferroics will tend to be oxides, simple oxides, some things like chromium oxide, iron oxide, common rust, or rather the black form of iron oxide called magnetite also is believed to have multiferroic properties. Simple binary oxide with a simple single metal bound to oxygen, all the way to more complicated structures that we call, for example, hexaferrite have 4 or 5 different metals in them, but they're still rather commonplace materials, and you can find them in fridge magnets if you want.
And so all of these materials that you've mentioned, they vary with complexity, but they could all potentially then have uses in things like data storage.
They could all have uses if we can, first of all, understand how they work, and this is part of what we're trying to do at Diamond, and also integrate with current electronic devices. This is the big challenge, particularly for applied research, because you have to essentially put these different types of materials on a chip that normally only has silicon and silicon oxide, and this is the big technological challenge.
Well, so as you mentioned then, you're looking into, I guess, some of the fundamentals of it to understand it a bit more. And, well, a key issue seems to be the actual temperature that these multiferroics have to run at in order to induce this change in the properties.
It is very much an issue, but we know that we already have materials that run at room temperature or even at higher temperature. Things like chromium oxide, for example, would have the properties at room temperature. But sometimes we also study materials in which these properties are displayed at very low temperature. These materials are the first one in which a new type of phenomenon or underlying principle of multiferroicity is manifest. And then they are the first models that we have to try to understand this phenomenon. This is why we focus sometimes on materials that only work for the moment at low temperature. And if we can crack the secret in a sense, then we can ask our chemist colleagues to find the right combinations of elements so that these materials will then be able to work at room temperature.
Well, at Diamond, you're using techniques such as X-ray scattering then to look at the particular structures or arrangements. What have you been able to find out then? What's been a recent, perhaps, discovery?
What we can do, for example, is directly see the changes in the magnetic structure as we apply an electric field. The arrangement of the magnetic moments in the crystal sets up a tiny electric field, and this responds to the external electric field. And as you move the internal field, the internal polarization of the crystal by an external force, then the spins follow. So you switch the spin system by applying an electric field. This is the ultimate goal of what we're trying to do. And if we could do that at room temperature in a material that is cheap and can be integrated in electronics, we will have reached the goal of our research.
Understanding then how these particular materials work and function and change their properties like that, what's it then hoped that they could be used for?
So we're hoping to use these materials to store information in a magnetic form and then to change the information, the state of information, say from 0 to 1 in a bit, but rather than doing it by applying a magnetic field, which is cumbersome and it cannot be really scaled down to very, very tiny dimensions, we could apply an electric field, which is much more localized. It has very low energy consumption when we put it in a device, and you can have a much more compact, faster, and overall better system.
Paolo Rodelli from the University of Oxford.
Did you know it took Dorothy Hodgkin 12 years to solve the structure of insulin? If she were to do this today on one of Diamond's MX beamlines, it would only take 15 minutes.
This is the April edition of the Diamond Light Source podcast, with me, Mira Senthi-Lingam. And this month, we're attracting your attention with magnetic forces as we explore the atomic nature of magnetism. But before we continue luring you down to the atomic scale, let's join Sarah Boundy from Diamond's communications team to find out what's been happening at the facility over the past couple of months, starting with a particularly notable visitor.
Yes, so in the middle of March we had a visit from David Willits, and he's the Minister for Universities and Science. He toured the synchrotron and met diamond scientists and representatives from some of our industrial partners. That included GlaxoSmithKline, Rolls-Royce, Evotech and Infinium UK. And whilst he was here, he officially inaugurated Phase 3. So that's our next 10 beamlines, which he said he was delighted to confirm the funding for. And he also said that Diamond is one of the really great scientific research facilities, not only in Britain, but around the world.
Well, it's good that he met some of the scientists that are based here at Diamond, because you've had some interesting papers published recently as well.
Yes, our publications database is going strong. We've now got over 1,250 published papers on there. A recent highlight is work carried out on I-22. That's our non-crystalline diffraction beamline. And the work was published in the American journal PNAS, the Proceedings of the National Academy of Sciences. And researchers from the universities of Manchester, Texas, Cardiff and Sydney used Diamond, as well as the European Synchrotron Radiation Facility in Grenoble, France, and the Advanced Photon Source in Chicago. And they were using the X-ray facilities to determine the structure of tropoelastin. That's the main component of elastin, which is what allows tissues in humans and other mammals to stretch. For example, when the lungs expand and contract for respiration, or when arteries widen and narrow over the course of 1 billion heartbeats, it's elastin that helps them to do this.
And what did they find out about its structure?
They discovered that tropoelastin is a curved spring-like molecule which can extend to 8 times its initial length and then return to its original shape with no loss of energy.
And I guess this could have some applications then in synthetic polymers to kind of make elastics.
Well, yes, elastics are used in applications as diverse as clothing, vehicles, tissue engineering and even space travel. So understanding how the structure of tropoelastin creates its exceptional elastic properties could enable the development of synthetic elastin-like polymers with potentially wide-ranging applications and benefits.
And as well as this research, there's been more developments in a topic we've covered in the past about metal-munching earthworms.
Yes, previously on the podcast we've heard from Mark Hodson from the University of Reading, who was looking at the potential of earthworms as eco-warriors, cleaning up toxins from contaminated soil. So he and his colleagues have published their latest findings using I-18, which is our microfocus spectroscopy beamline. They were looking at tiny granules, which are not quite 1 millimetre across, and they're granules of calcium carbonate, which is actually the main component of snail shell. Now, these granules are excreted by earthworms that have been living in lead-contaminated soil. So the group found that the excreted granules contained a substantial amount of lead, meaning that the earthworms are able to ingest the lead, which is then excreted out as insoluble metal carbonates, potentially immobilising the metal and making it less available to plants.
So giving them a use in lead-contaminated sites then?
The granules did pick up a lot of lead, but the problem is the granules are so small that they pick up less than 1% of the lead in the soil. So although the earthworms can survive in these toxic environments, the granules won't have a big impact on lead.
So what's next though? So what could they be used for?
Well, the next step is to look at different elements within the granules, such as strontium and zinc, and they might be concentrated more heavily and have more of an effect.
Well, as well as the papers being published by scientists working here, they do need access to beamlines. So what new beamlines have been developed?
So we've had first light on I-20, and that's our X-ray spectroscopy beamline, which is also known as LOLA. It's going to be our third spectroscopy beamline and 20th operational beamline when it comes online later this year. And I-20 will be used for chemistry, biology, environmental sciences and material sciences too.
Okay, so spanning a wide range of disciplines. And just lastly, I guess, what about outreach? That's something you're always doing here at Diamond.
At the end of February, we took part in the Oxfordshire Science Festival, and we've just got back from the Big Bang Fair in London. We had some great hands-on activities that helped to explain how our magnets work in the machine and what kind of research Diamond is used for.
And what about regular members of the public wanting to visit Diamond? When's the next Inside Diamond Day?
Well, the next Inside Diamond Day is coming up really soon, but as usual, it's already fully booked. The next available date is in June, and people can find out more on our website.
Sarah Boundy from Diamond's communications team. Now that's almost the end of this month's podcast, and so far we've had a good insight into magnetic fields, properties and materials. So now we hear about a group of materials that, in a recent paper published in Science, have been proven to have a certain type of magnet present. Explaining more, here's one of the authors on the paper, Professor Stephen Lovesey from Diamond Light Source.
When you ask yourself what is the property of a material which generates magnetism, it is the fact that you have broken the symmetry with respect to the arrow of time. There is another symmetry, and that is the symmetry with respect to the direction of space. And you can see this, for example, when you look at your hand in a mirror. Your hand is changed from being left-handed to right-handed, and this is a direct observation of the fact that you have changed the direction of space. When you combine both the breaking of the direction of time with the direction of space, you generate a very special type of magnetism, which is called the anapole. They're also called orbital currents, and the anapole has been thought to be most important in understanding a complex set of materials which are also able to conduct electricity without any resistance, so-called superconductors.
Just to step back a little bit there, so there are different types of magnets really. So there are the dipoles that people know with the typical kind of north-south divide, and then there are these anapoles.
That's quite correct. The dipole moment, for example, your compass needle, has the property that it does break the direction of time, the arrow of time in a material. It is also characterized by the fact that if you change the direction of space, it remains unchanged. The characteristic feature of the anapole is that they have the property that they also change their behavior if you change the direction of space. Now, these anapoles can only be observed with light. So if you take a material and you illuminate it with light or X-rays, it gives you a method of imaging these anapoles.
Now, you've been looking for the presence of these anapoles in high-temperature superconductors. These are materials that once they reach a certain temperature, they lose their resistance and are able to have electric currents permanently flowing through.
Yes, as you lower the temperature of a superconducting material, and some of the materials are extremely simple, they're elemental, then they lose the resistance to the passage of an electric current. Unfortunately, the temperature at which this desirable property comes about is very low. So in the practical application, say for the transmission of electricity over power lines, it's not a practical solution to an efficient transmission because you would have to have your cable at an extremely low temperature. The interest in this class of materials, which are called high-temperature superconductors, is that the temperature at which they have this desirable characteristic is much higher. It's almost at room temperature.
And now, well, these materials were discovered about, 25 years ago, but the workings of them are still very much not understood. And so this is what you've been studying. So it's thought that potentially these anapoles play a role in how they are able to have this property.
Well, 25 years on, what we have learned is that there is no single unique theory of these high-temperature superconducting materials. Each class of compound seems to have its own theory. But we still search for unifying themes. And one of the unifying themes that's been proposed is the existence of orbital currents, which hitherto I've been referring to as anapoles. The experiments that have been done at the Swiss light source by Valerio Scagnoli and Staub have shown very good evidence for the existence of the orbital currents in a prototype, high-temperature superconducting material, which is very simple. It just contains two elements, copper and oxygen. And the proof, the experimental proof, that the orbital currents exist now gives us greater confidence in pursuing the types of theory for which the orbital currents are an essential ingredient in the mix.
So the material that's been studied is copper oxide, which is really, I guess, a parent component of most high-temperature superconductors, because one example of a high-temperature superconductor is yttrium, barium, copper oxide. So the copper oxide is in there, and it's also in many others. So this is a good material to have studied.
Yes, I mean, it's good for two reasons. One, it is apparent. The second thing is it's simple.
So this has provided an understanding of the workings then of these high-temperature superconductors, or at least one aspect of them.
This is the first experiment of its type, and the evidence is extremely solid.
This finding, though, has repercussions in other materials as well as high-temperature superconductors.
Yes, the building block that I've been talking about, the anapole, the other area of interest where they appear are so-called multiferroic materials. And these are materials which are both magnetic, so if they respond to an external magnetic field, but they are also polarized electrically. So they have both a definite magnetic polarization and also a definite electrical polarization. And these materials too appear to be characterized by the existence of the anapole.
And so what next then, having found the presence of this orbital?
We will explore copper oxide still further, and the technique will be then used, if you like, on real high-temperature superconductors, which contain 4 or 5 elements, chemically much more complicated, because now we have a sure footing, a good understanding of how to do the experiments and how to understand the results of the experiments.
Stephen Lovesey, Professor of Theoretical Physics at Diamond Light Source and the ISIS Neutron Source in Oxfordshire. Now that is it for this month's podcast, but we'll be back in June with more research, news and events from Diamond. In the meantime, however, if you have any questions about Diamond or the research that you've heard about in this podcast, or else if you have any suggestions for what you'd like to hear more about, email podcast@diamond.ac.uk. Thank you very much this month to Steve Collins, Paolo Rodelli, Sarah Boundy and Stephen Lovesey. I'm Mira Senthilingam and thank you for listening.
The Diamond Podcast is brought to you by Diamond Light Source and produced by thenakedscientists.com. There's more information on our website at diamond.ac.uk/podcast.